All right, so welcome to the physics lesson today. We're going to be talking about impulse and momentum. So before I jump into things here, so I try really hard when I describe a new concept to make sure that I explain conceptually what the thing means, right? So like when we talked about displacement, we learned that basically displacement's a measure of how far an object goes, and velocity is basically a measure of how fast an object moves. And force, for example, is a measure of how hard something is being pushed or pulled, right? So there's most of the terms we've talked about have had these really sort of easy, kind of everyday explanations for them. Momentum is a little bit different than that. We're going to learn in the video today that momentum is mass times velocity. And I'll give you a conceptual definition, but ultimately that equation is going to be the best definition that you can get for momentum. So today's video, really we're going to focus on equations, more than I like to in general. So kind of bear with me through the lecture today, through the video today. You're going to get, a bunch of equations and kind of learn how to use them. And then over the next couple days in class, we'll sort of backtrack and talk a little bit about sort of why we care about these equations, how the equations help us understand the real world a little better, okay? So anyway, with that in mind, here we go. Momentum. Symbol for momentum is a lowercase letter p. Why they didn't use m? Well, m is mass, right? So I think they just sort of worked their way up the alphabet until they hit a letter that hadn't been used, and lowercase p was the next option. All right. So definition of momentum is inertia in motion, which for a lot of people doesn't make a ton of sense. Here's how I like to break it down. Check it out. One of the things we learned was that mass is a measure of inertia, right? And when you're measuring motion, you're measuring the object's velocity, right? So momentum, inertia in motion, we're talking about the mass of the object having some velocity, all right? So to have more momentum, you have to have more inertia, more mass, and more motion, more velocity, okay? And so, in general, an object that has more mass and more velocity has more momentum, all right? So here's the equation we're going to use to calculate momentum. It's just mass times velocity, okay? In shorthand, P equals mv. Momentum equals mass times velocity. All right. So let's do a quick example here. The main thing I want to talk about, the math is easy, but I want to talk about the units for a second. So suppose I gave you this. Suppose I told you a 5-kilogram object is moving at 4 meters a second. What's the momentum? Well, the answer is here on the board, but again, I want to talk about the units. So what you would do is you'd start, by writing down what you know, which is this. We know the mass of the object is 5 kilograms. We know the velocity is 4 meters a second. We're looking for momentum, right? So you go, oh, well, momentum is mass times velocity. Plug in your numbers, 5 kilograms moving at 4 meters a second. Gives you a momentum of 20 kilogram meters per second. Okay, and that's how you leave it. Unfortunately, there's not a shorthand way to write out those units. It just is what it is. It's 20 kilogram meters per second. Okay? Also worth noting is that if the object was sitting at rest, then the velocity would be 0, which would also make the momentum 0, right? So just be aware of that. You have to be moving to have momentum. All right. So moving forward, momentum depends on mass and velocity, right? And it turns out that because of that, it's possible for two very different objects to have the same momentum. I just realized I forgot to change a typo here. We're going to change the velocity of the cow here. Pretend this was 0.4. All right, I forgot my decimal there. Okay. So anyway, let's check it out and see if this works. Remember, momentum is mass times velocity, right? So we know our mass is 20 kilograms. We know our velocity is 8 meters a second. Multiply it out, and you get 160 kilogram meters a second, right? Okay, now the cow, on the other hand, has a bigger mass but a smaller velocity, and so the two kind of compensate for each other. Check it out. Momentum is mass times velocity. The cow's mass is 400 kilograms. The velocity is only 0.4 meters per second. When you multiply it out, you get, once again, 160 kilogram meters a second. All right? So it is possible for two different objects to have the same momentum. In this case, you can see you've got a cow that has a big mass and a little velocity, having the same momentum as a dog, which has a little mass and a big velocity. Okay? All right, so It is worth noting, for example, that if the dog changes his velocity, his momentum changes, right? Look, the dog's mass, realistically, the dog's mass is not going to change, right? Okay, the only thing that you can really change about an object is its velocity. Okay, so the only way that you can change momentum is by changing the velocity, right? So, in this problem, the dog had a mass of 20 kilograms. Let's suppose he had an initial velocity of 8 meters a second. All right, and then let's suppose he sped up to a final velocity of, I don't know, whatever, let's say 12 meters a second. It doesn't matter. All right, but the dog is speeding up. So now he's got an initial velocity and a final velocity, right? Well, because of that, he's also going to have an initial momentum and a final momentum, right? So his initial momentum would be the mass times his initial velocity, which we found on the previous slide. That's 160 kilogram meters a second, right? His final momentum would depend on his final velocity. So that'd be mass times final velocity, right? So his mass is still 20 kilograms, but now his velocity is 12 meters a second, right? So now his momentum is 240 kilogram meters a second, right? And so as a result, what just happened there is his momentum changed, right? So we could, if we wanted to, find our change in momentum. That would be final momentum minus initial momentum, right? And we'd just subtract these two guys, right? We would take the 240, subtract the 160, and in this case, we'd end up getting, what, 80 kilogram meters a second just by subtracting. Basically just telling you that the momentum increased from 160 up to 240, increased by 80. All right? So why do we care? Well, let me show you why we care. Oh, shoot. Arrgh. There we go. It turns out that you can do a little bit of algebra here. Change in momentum is final momentum minus initial momentum, right? So remember, final momentum is just mass times final velocity. Initial momentum is mass times initial velocity. You can do a little bit of algebra here, factor, and get this, okay? So there's change in momentum. That equation is going to become important in a little bit, okay? So there we go. Right now you're looking at this equation going, why is he telling me this? Bear with me for a second. What we're going to do is we're going to come up with a new equation that allows us to think about some things in a way that we hadn't previously thought about them before. So just kind of write this down and kind of keep it in the back of your head, and we will come back to that in a minute, okay? The big thing, I guess, that you should be understanding right now is that in order for your momentum to change, your velocity's got to change, right? Okay, so moving on. All right, so what we're going to do is we're going to solve this example, this problem that's on the board here. We're going to solve it twice, once using Newton's laws and then once using some new equations that I'm going to show you. All right, so it says, suppose a soccer ball with a mass of 0.75 kilograms is rolling towards Roy at 16 meters a second. Roy is going to kick the ball back the way it came from. In doing so, his foot exerts a force of 180 newtons on the ball for 0.15 seconds. And we got to find the ball's final velocity. And so I sort of broke it up into steps for you. All right, so write the problem down. Okay, and let's make a quick drawing. All right, so here's the idea. Here's the ball. We know the mass of the ball is 0.75 kilograms. It's rolling towards Roy at a velocity. We're going to call that initial velocity, because that's the velocity of the ball before he kicks it. The velocity was 16 meters a second. Okay, here's Roy. Whoa, I don't know what's going on with his hand there. But, okay, so he's running. He's going to kick it this way. So here's the force of Roy, 180 newtons. At this point, hopefully you're looking at these two arrows and going, oh, one of them is in the opposite direction. So because of that, we got to make Roy's force negative, right? Because in math class, we do positive, negative, positive, negative. So this guy is negative, right? Okay, and then it tells you that his foot is in contact with the ball for a time of 0.15 seconds. Okay, so part A says make a free body diagram. So there, we've done that, right? Technically speaking, I should put in my force of gravity and my normal force, but I'm not going to worry about those because they cancel out. All right, so this was just sort of designed to get me thinking about it. All right, part B says find the net force. Well, the only force affecting its motion is the force of Roy. So there's our net force. We're going to, as usual, assume no friction or air resistance just to keep things simple. Part C, find the acceleration. To do this, we need to think back to Newton's second law, which says acceleration is net force over mass. If it's been a while since you thought about that equation, it would be worth writing down again, because it will come up now and again this chapter. Okay, so our net force is negative 180 newtons. Mass of the ball was 0.75 kilograms. Grab your calculator and divide it out, and you get negative 240 meters per second squared. So now for part D, we can find our final velocity. Final velocity is initial velocity plus acceleration times time. So our initial velocity is 16 meters a second, plus the acceleration is negative 240. It's a big acceleration, isn't it? Because the velocity of the ball changes a lot in a small amount of time, specifically 0.15 seconds, right? So you end up getting 16 meters a second minus 36 meters a second. And so you end up getting negative 20 meters per second. Okay, so there is the ball's final velocity. So after Roy kicks it, it's moving back this way at 20 meters a second. Okay, so that's how we would have solved that problem when we learned Newton's laws. We're going to learn another way to do it. And to be honest with you, the other way, I honestly don't know that it's really any easier or any harder. Again, ultimately, this is going to be important because it's going to help us understand some equations. All right, so kind of bear with me here. I'm going to go over my 15 minutes. I will keep it under 20. The big thing I want you to get out of this is that it works. The equations I'm about to show you give you the same result. All right, so we're going to solve this problem again using some new equations. Hopefully, if everything works the way we want it to, our final velocity will once again be negative 20 meters a second. All right, so here we go. So before we do it, we got to come up with these new equations. So we already know two equations for acceleration. Okay, they can be used to generate two new equations related to momentum to give us another method to solve these problems. All right, so here's the two equations I'm thinking about. We know that acceleration is Vf minus Vi over t, right? If we wanted to, we could shorthand that and write it as change in velocity over time, right? Cool. So that's from the first chapter of this class. We learned that. All right. Then when we did Newton's laws, we learned that acceleration was net force over mass, right? So now what we've got is we've got A equal to two different things. So using a little bit of math, right? If A equals B and A equals C, then B equals C. So I can set these two things equal to each other. So what we know now is this. Change in velocity over time is acceleration. That's the same as net force over time, which is also acceleration. Oh, no, sorry. Mass. Okay. So from math class, hopefully you remember if you have two fractions that are equal to each other, you can cross multiply. So I'm going to multiply these two guys, and I'm going to multiply these two guys and set them equal to each other. And here's what you get. Net force times time equals mass times change in velocity. All right? That is huge. Let me see here. Okay, so what we found a couple slides ago, we figured out that this mass times change in velocity was our change in momentum. That's how much the momentum changes by. Okay? This guy, net force times time, is what's called impulse. Okay? Unfortunately, there's not a good definition for impulse. This is part of the reason I'm not going to focus on the concepts. The definition of impulse is force times time. All right? So I usually just tell my students that impulse is the same thing as change in momentum, which is what this equation says, right? It says impulse is change in momentum. Net force times time equals mass times change in velocity. Okay? So again, I don't want to get bogged down with the concepts right now. What I do want to focus on is this equation. which allows us a new way to solve problems, okay? I guess the only thing that I would add on is, in order to use that equation, you also have to know this little fact, which I think hopefully you all do. Okay. In fact, sometimes I see people do a substitution and they'll rewrite that equation up at the top like this. Net force times time equals mass times VF minus VI. Okay. In fact, why don't we do that? Let's just use that. Okay. All right, so what I'm going to do now is I'm going to go back and solve that last problem again, but using our new equation, all right? So suppose a soccer ball with a mass of blah, 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 blah. It's the same problem, all right? So let's write down what we know. And again, I would make a drawing. I'm going to skip the drawing in the interest of time because we already made it. But so when we made that drawing, here's what we figured out. We figured out that the mass of the ball was 0.75 kilograms. We figured out that the initial velocity was 16 meters a second. And that the force acting on the ball was negative 180 newtons. That negative sign is why I want you to get in the habit of making drawings, you guys, because you'll miss negative signs if you don't make drawings. Okay. We know that the time is 0.15 seconds, and we're looking for our final velocity, right? So let's do it. Here's what we know. Net force times time equals mass times change in velocity, or net force times time equals mass times VF minus VI. All right, so most of the problems that you're going to see on your next assignment are going to have these 5 variables in them, and I'll always give you 4, and you'll have to find the missing one. And that's all we're doing here. It's just some algebra. All right, so let's plug in our numbers. Net force is negative 180 newtons. Time is 0.15 seconds. Oops. Equals mass, 0.75 kilograms. Final velocity minus initial velocity was 16 meters a second. And solve it. Okay? Now, I'm going to do something that will make most science teachers cringe, and that's this. I'm going to rewrite it again without the units. All right? Check it out. All of our units are metric, right? We got newtons, seconds, kilograms, meters per second. That's all metric. Our final velocity has to be meters per second. It's the only possible option. All right, so I'm going to rewrite this again without units. I think it'll just make it look simpler, and then solve it and just tack the units back on at the end. All right, so here we go. Let's multiply it out, or let's write it with no units rather. So you get negative 180 times 0.15 equals 0.75 times VF minus 16. Right, that looks much simpler, doesn't it? Okay, so here we go. Let's multiply this whole thing out. You're going to get negative 27 equals, now over here you got a couple options. You can either divide by 0.75. For whatever reason, I always feel like I need to distribute, so that's what I'm going to do. Distribute, distribute. So you get 0.75 VF minus 0.75 times 16 is 12. Cool. So add 12 to both sides, and you get negative 15 equals 0.75 times VF. Divide both sides by 0.75, and you get negative 20 meters per second equals VF. All right, why are we happy? Because that's the same answer we got last time we solved it. All right, so again, conceptually, what's going on there is a little more complicated. The big thing I want you to understand is that we started out with this new equation here, either of those, right? And we got the same answer, so we're happy. That means that this equation does, in fact, work. All right, so here's what we've learned. Momentum is the product of mass and velocity, right? Product means multiply, mass times velocity. Impulse is just a change in momentum. And here's our equations, right? And then actually we added on, we replaced this bottom one with this. Okay, so you might add that to your list. All right, so in the minute that remains, oh no, we're going to solve this. So take a second, write this down, read it, and try to solve it. Do it before I do it. Actually try it. Okay, now I'm going to try it, assuming that you've solved it. All right, so start by writing down what you know. We've got a 40-kilogram shopping cart rolling towards your car. So here's your cart. We know the mass is 40 kilograms. It's rolling towards your cart at a velocity of 18 meters a second. It tells you you've got 3 seconds to stop it. So our final velocity is going to be 0. And the question is, how much force do you need? Right? So we're looking for our net force. Okay? So net force times time equals mass times VF minus VI. Plug in your numbers and solve it. Okay, so our net force is what we're looking for. Time is 3 seconds. Mass is 40 kilograms. Final velocity 0. Initial velocity was 18 meters a second. So 0 minus 18 is negative 18 times 40. This gives you negative 720 kilogram meters a second. Over here, net force times 3 seconds. Again, if you want, you could have just dropped out your units. Divide both sides by 3 seconds. And your net force is negative 240 newtons, because it's metric. Okay? So tomorrow we'll talk more about the concepts. I've gone over by 20 seconds. I'm stopping. Have a good day.